All right. Well, let me then just briefly recap what was covered in those lectures, and then I'm just going to give a lecture on nonlinear diffusion today, and the application of multiple scales to traveling wave solutions. So we're sort of deep in the throes of traveling wave problems. So not really last time, but before Ian's lecture, we had talked about linear wave propagation, and that was kind of the recorded lecture for that happened before last Friday, and so the point there is that if you have some sort of linear wave equation, like we just took the classical wave equation and added some friction to it, you could solve this explicitly, but it's hard. And so a perturbative solution or an asymptotic solution can be obtained using multi-scale methods. And what we found is that essentially you're going to have solutions to lowest order require multi-scale coordinates, in particular of the form theta plus equals x plus t, theta minus equals x minus t, t2 equals epsilon t. These are now these long time scale coordinates, and the stretch spatial coordinates. So so U then can be approximated to first order as some function of these characteristics, the characteristics of the classical wave equation, x2 and t2. And then up to next order would be U1 and so on. And what we found in general, that U0 is actually just a function of T2. That's sufficient. And our general solution to the wave equation now, instead of it just being a function of the two characteristics added together, it's a function of the two characteristics and this slow time scale. So you're going to have some slow time scale modulation of the terms involving each of the characteristics. And in particular, to eliminate the resonant terms, okay, where you can have resonance here, right, because you have a second order time derivative, a second order spatial derivative here. So in order to eliminate the resonant terms, okay, you're going to have to require that d2 dt 2 plus 1 f0 is equal to 0, and then also 2 dt2 plus 1 g0 is equal to 0. Okay, and this comes from the order epsilon equation, basically in your hierarchy. By plugging this in, you enforce that you have no resonant terms, and this leads to finally that U is approximated by a half f of x plus t, right? Because that's your one characteristic. F of x minus t, that's your other characteristic. E to the minus epsilon t over 2. Okay, and in fact, this is exact. And if you plug it in, it works out as the exact solution. So what does this look like to you? I mean, it looks exactly like what you would get from D'Alembert's solution, if you remember back to PDEs, right? Just your typical, take your initial condition, propagate it right, or propagate half of it right, propagate half of it left, and now this friction term is going to dampen things down. And this arises essentially from this resonance elimination condition, okay? And so for the homework, you basically have to do this again, except in the case of a non-trivial initial velocity, okay? Now, the other part that we talked about, well, that I talked about in the previous lecture, was nonlinear waves, okay? And for that, we took the Klein-Gordon equation. The example here was, so this is kind of a long recap, but I guess that's kind of, because it's been maybe a long time since you looked at this, like a week or so. The idea is, let's say we have something like a wave equation, and then this is sometimes called a physical term involving some elastic foundation for the string, and then you have some nonlinearity here. And essentially what you should expect is to have wave type functions to first order, okay? And a wave function looks like e to the I kx minus omega t. And if you plug this in, then you find that to leading order you get u is u0 kx minus omega t plus some epsilon u1, blah, 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 okay? But this regular perturbation expansion does not work, okay? Basically because of secularity again. You're going to get resonant terms, and it's going to cause these solutions to sort of build up in amplitude over time, which is non-physical. It doesn't properly, you know, it conserves energy in a way which doesn't match the original problem. And so then in general, what you have to do is use multiple scales, not surprisingly, maybe. And you have theta equals kx minus omega t, y equals epsilon x, and then we'll take tau equals epsilon t. U is then going to equal something like u0 theta y tau plus epsilon u1 theta y tau, and so on. And in this case, okay, plugging in, expanding, isolating powers of epsilon, okay, you get the following amplitude equations, okay, for r equals omega y plus kappa tau. This is sort of like the slow or stretched scale characteristics now. S equals omega y kappa tau, okay? This is like taking your characteristics, right, and multiplying them just through by epsilon. We find that we have for u0 is equal to ay tau cosine theta plus phi y of tau. And we have this amplitude, and we have a phase. And in order to remove secular terms, we're just going to develop differential equations for this amplitude and this phase function. And so in general, we find that dRA is equal to 0, and dr of phi is equal to minus 3 over 16 omega Ka squared. Okay. And so that means that at the end of the day, what we find is that if let's say u0 of theta y0 is equal to alpha cosine theta, and d theta u0 theta y0 is equal to minus alpha sine theta, then a of omega y is equal to alpha, and theta 0 omega y is equal to 3 over 16 K A squared y. Okay. All right. So I know I'm rushing through this. This is all in the previous lecture, but I'm trying to build up to what we're going to do today. And what you find at the end of the day is that, okay, you just get something like u is equal to, or approximated by, cosine kx minus lambda omega t, where now lambda is equal to 1 plus 3 epsilon alpha squared over 8 omega squared. Okay. And in particular, the thing that we're interested in here is the phase velocity, which is VPH is equal to 1 plus 3 epsilon alpha squared over 8 omega squared, right? Everything that's in here times omega over k, okay? Because if I want to factor this out, if I want to factor out a k over omega here, okay, then I'll get something like, you know, k over omega times x minus VPH t. And this tells me that for larger amplitudes, you get faster waves, okay? And so unlike in linear wave problems, the nonlinear term in this Klein-Gordon equation makes it so that larger amplitude waves are going to move faster. And this is a property that you're going to get from nonlinear equations that you don't necessarily get from linear wave equations. Okay, so that was the last lecture in about 10 minutes, sort of in a nutshell. Okay. All right. So today, in the time that we have left, I'm just going to go through nonlinear diffusion. Okay. I had a little something prepared on wave-wave interactions. If you want to read that, it's just the other section. I think in this part of Holmes. So that comes between the initial wave equation and then this nonlinear diffusion part. Okay, so let's talk some about nonlinear diffusion. Okay, we brought this up in the PDE course. Okay, where we have some you know, time derivative of some substance or population. Okay. It evolves according to diffusion, and then there's some local reaction term, okay? And in the PDE course, we said, well, this could be like a logistic growth term. So maybe you have animals reproducing, and then they move about according to diffusion. This could be some autocatalytic chemical reaction, okay, that sort of a chemical reproduces itself and then spreads out in some medium, okay? And initially you start with some initial distribution, and I'll call this whole initial value problem dagger. So it can evolve, okay, to traveling wave solutions, okay, and we're going to look for, you know, stuff happening like this, where you have some high population or concentration invading, okay, and moving to the right. And then here's your low population or concentration, okay? You can also get this with models of spatial pandemic. So you know, if you just have some population that's spreading a disease according to local interactions, okay, and individuals only move according to diffusion, you know, they don't get in cars and airplanes and drive away, but they just sort of move, you know, by very local means. The only way that they can spread the disease is by these local interactions, and then it'll just sort of spread spatially across the population. And you see that sometimes when you have restricted movement, okay? So in order to get solutions like this, you assume that f of u is smooth, okay, on u goes from 0 to 1, okay, and it's going to be positive for u goes from 0 to 1. We'll make even more stringent restrictions that f actually is going to have roots at 0 and 1. F prime of 0 is greater than 0, and f prime of 1 is going to be less than 0, okay? So if you want to have a specific function in mind, let's take the quadratic u times 1 minus u, okay? And this is often what's called the Kpp equation, just the first letter of the, you know, three people's initials there. And this is akin to like local logistic dynamics, okay? Now, if you haven't seen the logistic equation before, okay, or if you don't remember it, I guess, because you probably usually see this in differential equations, right? The logistic equation, right? You can solve it explicitly. Du dt is equal to u of 1 minus times 1 minus u, right? You have an unstable fixed point here. You have a stable fixed point here. Okay, this is u. This is like your phase line, and essentially you increase, you know, population or concentration to u equals 1, this fixed point. So if we look at how this is going to evolve over time, right, u is a function of time. If you start off here, you're going to saturate to this upper level, right? And what typifies logistic growth is that you assume that, for example, if it's a biological population, there's only so many resources available to that biological population, whether it's bacteria in a dish, humans on a planet, or, you know, animals in some environment with finite resources. Okay, eventually they're going to run out of resources and they can't keep reproducing. And so this is like the carrying capacity. You rescale everything so that it's 1. So the idea then with equations like this is that once you have diffusion, you're going to obtain this maximum value, okay, throughout some spatial domain. But the way that reproduction will happen is that it will sort of invade into different regions. So, which is why sometimes you call these solutions invasion fronts or something like that. So, you know, whatever analogy helps you best, you could think of this as, you know, an invading epidemic or a biological populations, you know, spreading out and growing across a habitat or environment, okay, or a chemical reaction, okay. That's the idea here, okay. The other thing is that we assume that g of x is going to be smooth, okay. That's our initial condition. And g of x will, let's say it'll be between 0 and 1. And we'll say that g is going to go to 1 as x goes to minus infinity, and 0 as x goes to plus infinity. So that's kind of a sloppy minus infinity. Okay, as x goes to minus infinity. Okay, fine. All right, so for example, let's take for simplicity, g of x equals 1 over 1 plus e to the lambda x, and lambda will sort of control the steepness of this. Lambda is greater than 0, and we'll just go ahead and set up really an invading front. So this would be, you know, your g as a function of x. Here's your x axis, right? And so this is 1 up here and 0 down here. So the idea is that we have some, you know, full carrying capacity population, and it's moving into some empty region over here. Okay, it's just going to spread its way in. Okay, and so an invading front is going to connect two steady states. Okay, u is equivalently 0 and u is equivalently, u is equivalently 1 and 0. Okay, because f of 0 equals f of 1 equals 0. And if you go back to the original equation and you plug either of these in, it's a solution. So if you start out here, that's a solution, although it's unstable. If you start out here, that's a solution and it's stable. Okay. Now in PDEs, when we did this, we just said, what's the asymptotic traveling wave solution? The asymptotics are going to allow us to track the approach to that. Okay. So what do you think we're going to do? What method do you think we're going to have to do in order to get that? Method of
multiple scales.
Multiple scales, yeah. Okay. So this is our last foray into method of multiple scales. Okay. So in order to get that, okay, we're going to assume 2 time scales. Okay. And, you know, you could use an additional spatial scale. You don't need it here. Okay. We're just going to assume that we have an additional time scale that's going to sort of slowly modulate the shape of the front in the direction of the asymptotic shape of the front. Okay. So if we make these assumptions, right, we have dt plus epsilon d tau then of u is equal to epsilon uxx plus f of u. Okay, so it's just going to modify this total time derivative here. And then, of course, we need to write u now as not just x and t, but also tau. Okay. And then what do we do, right? We plug in, we expand, we match powers of epsilon, we eliminate the secular terms, right? And we see what we get for our first term expansion. Okay, so at order 1, we have dt u0 is equal to f of u0, and then also u0. Remember our initial condition of x 0 0 is equal to g of x. Okay, that's this little sigmoidally shaped function that we set up. Okay. Now we can solve this. We can use separation of variables to solve this because it's really just an ODE in time. Okay, and we get that the integral from 1/2 to u0 of dr over f of r is equal to time plus function theta of x plus tau that doesn't depend on time. And theta of x0 then, if I plug in tau, is going to be equal to, well, now I'm going to pull in my initial condition, g of x dr over f of r. Okay, so that's just applying this initial condition now to this formula. So we get an expression now for u, which is that u0 equals some function big U of t plus theta of x plus tau, okay, where the integral from a half up to u0 of dr over f of r equals s is going to determine u0 of s. So we only have the solution implicitly, okay? If we had a specific form of f of r, we could probably get this. For instance, like our quadratic, we'll do that at the end, okay? Now, we need more information about theta of x tau. We're going to get that at order epsilon. So dt u1 now is equal to f prime of u0 u1 plus dx squared u0 minus d tau u0, okay? And we can use equations above to manipulate this expression on the right-hand side a bit. So we have f prime of u0 u1, okay, plus now f of u0 theta xx minus theta tau plus f prime of u0 theta x squared, okay? And note from above, we have that f prime of u0 is equal to dt log of f of u0, okay? So we can solve for some expression for u1. u1 is equal to a of x tau plus t plus theta, theta xx minus theta tau plus theta x squared log of f of u0 all times f of u0, okay? And now the way that we restrict secular terms now is that we look at the expression that we have now for u1, and we pick out the terms that we need to eliminate that we don't want to grow large over time. Okay, so we have to carefully restrict theta to remove our secular terms. Okay. And so note that, first of all, as t plus theta goes to positive infinity, okay, there is no divergence of f of u0 log of f of u0, okay? So as you take this limit, right, f of u0 is going to go to 0 in this case. And so this is going to go to 0 faster than this goes to negative infinity. Okay, if you do out L'Hopital's rule or whatever. Okay, so this is since f of u0 is going to go to 0 in that limit. Okay, but when you go back the other direction, when you go to t plus theta, okay, goes to in negative infinity. Then u0 goes to 0, and log of f of u is going to be approximated by kappa t plus theta in this case, where kappa is equal to f prime of 0, which is going to be greater than 0. So this produces a secular term in this case, which implies that in this limit, right, if we go over here, as this gets large, right, we're going to pick up this term in the t plus theta goes to minus infinity limit. So we're going to have t plus theta out in front here. And we can also approximate this by this term kappa t plus theta. So we're going to have three terms that involve kappa t plus theta, or sorry, t plus theta in that case. That's going to form a partial differential equation or operator that we're going to need to set to 0. Okay, so this means that theta xx minus theta tau plus kappa theta x squared is going to be equal to 0 in order to eliminate that secular term now. Okay, now this seems annoying because, oh well, it's a nonlinear PDE, right? But it turns out you can change variables and take w of x tau is equal to e to the kappa theta x tau, and that'll actually turn this into just the heat equation, wxx equals w tau, okay, where x lives on r, and yeah, tau is positive. So then you can just solve for w, and you get h of x plus 2r tau e to the minus r squared dr, where h of x is equal to whatever the initial condition is for wx. And we can figure out what that is from theta of x0. It's going to be the integral from 1/2 to g of x of d of r over f of r. Okay, theta of x0 is going to be that. And if we plug that into w of x0, then we get that h of x is equal to the exponential of the integral from 1/2 g of x d of r over f of r. Okay, so we have an initial value problem for w of x that we were able to solve. Okay, and we have this initial condition that we can impose. Okay, so I'll just note that you can show that h of x is well behaved. Okay, and this is an example in Holmes 3.10. I won't go through that. Okay, but essentially what we found is that to first order, u can be given by u0 of xt tau, where the integral from 1/2 up to u0 dr over f of r is equal to t plus 1 over kappa log of this w of x tau, where w is given by this along with this. Okay, so you say, oh, well, that's still pretty complicated, right? Because I still would need to be able to perform this integral, right? And then I have to perform this integral, okay? But we can make it a lot simpler in some specific cases. In particular, we can take the case of the logistic equation, and then we'll finally arrive at something explicit. And the nice thing about this then is that we can figure out the varying traveling wave velocity. And it actually tells us something about this sort of minimum speed that you expect to get from the Kpp equation, or some people call it Fisher's equation. Okay, so it's another way to kind of get this this minimum speed equation result, minimum speed result that people often get for Fisher's equation. Okay, so but basically your kappa here, right, is f prime of 0, right? And so you pull this out of your function. This actually this involves your function as well. So you would need something that's integrable in order to get something explicit for your solution. And so let's take a look at, in particular, for the Kpp or Fisher's equation. Okay, we'll take f of u is equal to u times 1 minus u. Okay, and this will be our example now. Okay, and in this case, u0 is equal to u0 t plus theta x of tau. Okay, and by integration, we can show that u0 of s is equal to 1 over 1 plus e to the minus s in this case. So we have this nice smooth sigmoidal function that we get for the profile of this. And remember, how is u of s defined? Okay, it's probably way up here. It's just given as the implicit solution to this integral formula here. So you can imagine how that goes. You plug in r times 1 minus r here. You perform partial fractions. You do the integration. You get some logs, right? In order to undo those logs, you exponentiate. You isolate u0, and you get back this function here. Okay. So that means that u0 is equal to w of x tau divided by w of x tau plus e to the minus tau. Okay. Because remember, w of x tau is given by e to the kappa theta here. So if you plug that in, it's going to be that kappa theta is going to be equal to log of w, and that'll just end up being exponentiated, and so you'll get these w's out of that. Okay, so this is our expression now. We just need to figure out what w is based on the formulas that we derived. Remember that w of x tau, okay, is going to be equal to this integral expression here, okay, that we got just by solving the heat equation and applying this initial condition. So in this case, w of x tau is equal to e to the minus lambda x square root of tau over pi, integral from minus infinity to infinity, e to the minus tau times s minus 2 lambda ds. If you work this all out, you just get e to the minus lambda x plus lambda squared tau. And because you pick up this Gaussian in here, so that eliminates your pi there out front from that Gaussian integral. And so at the end of the day, what you have is u is approximated by 1 over 1 plus e to the lambda x minus 1 plus lambda squared epsilon times t. Okay. So the tau sort of leaks in here as modulating the wave speed, right? You could factor out a lambda here, and you would have something like lambda times x minus a velocity times t, okay? And remember that lambda is specified in the initial condition. So all your parameters are specified for this, right? Your epsilon should be specified by the initial value problem. So what you have here is a traveling wave with a velocity, okay, given by what? Well, if I factor out this lambda, I'm going to get x minus lambda times x minus 1 plus lambda squared epsilon t over lambda, okay? So my velocity is going to be v is approximately 1 plus lambda squared epsilon over lambda, okay? And so you can find the minimum wave speed, which is actually going to be given by optimizing this function, okay? So if you minimize v of lambda, okay, to find that the minimum speed is going to be v min equal to 2 times the square root of epsilon, is going to occur for lambda equals 1 over square root of epsilon, okay? So depending on your choice of initial conditions, okay, your choice of initial conditions are actually going to shape the speed of the waves that you have, okay? So it's not necessarily like the bistable equation or some nonlinear equations where you just have a single type of traveling wave that you can get. The speed of the traveling wave, initially at least, is going to depend on the way that you load up initial conditions. And the way that you get the slowest initial wave is to choose this as your sort of gain of your initial condition, how steep your initial condition is, okay? And then as you change that, you'll get faster waves on either side of that, okay? But essentially what you should find, right, is that this, at least to the order of that we've expanded to, at least a first order, right, you have a traveling wave with constant speed, okay? But that speed is determined by the initial condition in this problem, okay? So you start off with something like this. Let's say at t equals 0, and here's your x, right? And then you get this invading front that just keeps moving along, okay? So t equals 5 here, and then t equals 10 here, okay? And it travels along at a speed that's given by v of lambda. And if you notice this, right, this is perfectly a traveling wave solution, right? It's not, its amplitude isn't modulated or anything. So basically, you're just taking this initial profile and just sort of moving it along, okay, at a constant speed that's given by this expression here, okay? So just to recap, okay, and that's it for this lecture. What we did, right, is we suspected that this problem with nonlinear diffusion was going to introduce an additional long time scale, okay? And indeed, by introducing that additional long time scale, when we expanded out to order epsilon, we were able to take these, I'm jumping around here. Yeah, we were able to take the secular terms that emerge in the next order term in the expansion and essentially eliminate them, right? We looked at the two ends, right? One end is going to occur where when you take t plus theta goes out to positive infinity, but then all of this is going to vanish, and so it's not going to affect this, okay? But then in the limit as t plus theta goes to minus infinity, you have this competition between f of u0 going to 0 and log of f u0 going to 0 that's going to cause this to give you some constant term, which is going to be f prime at 0 there, okay? So once we introduce that, okay, and then what we find is that we have this secular term elimination equation here, and this PDE can be solved to give you this expression W that's going to account for sort of the slow timescale modulation of this traveling wave, okay? When you look at a specific case like the Fisher equation here, what you find is that specifically this is just going to slightly change the speed of your traveling wave, okay, according to this expression lambda squared epsilon here, okay? And so, you know, in the limit as epsilon goes to 0, you just have a traveling wave that travels at speed, yeah, I guess 1 over lambda in this case, okay? But yeah, once you introduce this diffusion term, then this is the modulation that you end up getting for your speed, and you sort of recapture this minimum wave speed result that you can get other ways, like using phase plane analysis or something like that for Fisher's equation. Okay, so that's the case of nonlinear diffusion. Any questions about that before we wrap up for today?
I have kind of an unrelated question, just on the homework for, like, I think it was the last question. You have the resonance condition with omegas in it. Should that be with C's instead of omegas?
Oh, maybe so. Yeah, let me see. Is there a typo in the homework? So the wave quartet should it be?
Because I think at least the example that Ian went through, you had like C1 plus C2 plus C3 was equal to 0. So I assume that this condition was analogous to that. And then working through at least like the first part, all the omegas canceled out anyway. But it's also possible I just did it wrong. So
I think you're right. Yeah, maybe that's just a typo in the formulation of the problem. Yeah, I think you're right. Yeah, let me double check with Ian, because he gave me this problem. So
okay.
yeah, I want to make sure. But yeah, that sounds like those should be C's. Yeah, but in particular, do you have to show anything about that resonance condition, or is it just that's just
You need it to, well, I mean, I did it with assuming there should be C's, but you need it to prove the energy conservation thing in part A.
Yeah. Yeah, I think you're right. Yeah. Why don't you work off that assumption that you replace the omegas with C's in that resonance condition. Yeah. Okay. All right. So well, if there's nothing else, so I'll just say, yeah, I won't record a lecture for Friday. I'll just give you all the day off on Friday, and then yeah, we'll be back to lectures on Monday. And then yeah, office hours will be as usual on Monday and Tuesday. So we're gonna switch to a slightly new topic, the WKB method, and then the last part of the course after, we'll do sort of a couple weeks of WKB method and a short homework on that, and then the last part will be on homogenization, and then I'll do some just additional kind of PDE examples, just sort of a sampler of other examples from asymptotics. From my own research and otherwise. So, and then we'll wrap up. So I think we only have about another 4 weeks left of lectures, and then you'll do project presentations the last week of class. So. All right. Well, have a good wellness day tomorrow, and then have a good day off from this class on Wednesday, and Friday, and then I'll see you guys on Monday.
Thanks, Zach.
Thank you.
Take care. Bye.